Hi, my name is Doug Summerlin, and as part of my graduate studies at the University of Maryland this semester, I took a course called ENPM701, Autonomous Robotics. In this course, we were tasked with constructing and programming a vehicular robot to complete a pick-and-place challenge in a 10 by 10 foot arena completely autonomously, with no real-time assistance from an operator. This course really tested my ability to apply foundational principles of robotics, such as modeling, kinematics, computer vision, and control theory, in a practical scenario. In this video, I'm going to demonstrate the process I followed in creating this robot, which I named D.A.R.T for Detect and Retrieve Timely, and I'll demonstrate how I did in the grand challenge at the end of the semester. I hope you enjoy.
To prevent myself from going crazy with cable management and small tweaks to the orientation of the camera sensor, I decided to just design a couple of 3D printed mounting plates that I could use to fasten to the robot chassis. And this made cable management a lot more convenient and iterating on the design a lot more convenient. With those parts printed, I could begin assembling the robot with the kit provided by the instructor. The chassis of the robot was equipped with 4 DC motors, 2 of which were instrumented with a magnetic encoder, providing a resolution of 8 pulses per rotation. Once the motors were correctly housed in the chassis and the wheels were mounted to the motors, I began to integrate the other parts of the assembly, which would be the servo gripper, the custom 3D printed mounting plates, the power supply units, and the other electronics. With most of the robotic assembly integrated at this point, I then shifted my focus to supplying power to the different components of the assembly to make sure that everything was functioning properly. This was definitely one of the most exciting parts of the whole process because it really felt like D.A.R.T was beginning to come to life. In total, D.A.R.T is equipped with a Raspberry Pi for central processing, an Arduino Nano to interface with peripherals, a camera for computer vision, rotary encoders to track odometry information, a sonar sensor for localization, an IMU to track absolute orientation, a power supply to supply power to all of the motors, and then a servo gripper to pick the objects out of the environment. For completely autonomous applications, it's absolutely imperative that the robot be able to follow a predefined path with minimal deviation. Here, in the case where there's no controller implemented, it's evident that the robot is not following the linear duct tape path correctly, and the error accumulation between the left and right motor encoders is gradually increasing over time because of the lack of implemented control. To correct this, I implemented a PD controller which compares the error between the left encoder and the right encoder and then modulates the effort of the right motor correspondingly to ensure that the robot follows a straight path. This capped the error between the left and right encoders to a maximum magnitude of 8 pulses. Now that the robot could follow a straight line accurately, I had to ensure it could turn accurately as well. So here I'm trying to make a rectangular box pattern with the robot, but here I'm not using the IMU feedback and just trying to rely purely on the encoders. As evidenced by the localization graph shown, it did not follow the rectangular pattern of duct tape very well at all. This kind of accumulation of position error would make any kind of accurate motion control in the Grand Challenge arena absolutely impossible. So we had to integrate an IMU sensor to give the robot some kind of absolute feedback on its orientation. And as seen here, upon implementing the IMU sensor into the control algorithm, the robot is following the rectangular path defined by the duct tape way more accurately, and its localization data is leagues better. To achieve this accuracy on rotational movements, I implemented a PID controller, which allowed me to compensate for overshoot caused by rotational inertia and achieve nearly zero steady state error at the end of the rotation. To identify obstacles in the Grand Challenge arena, we used the HSV masking technique to identify the colors of the obstacles in the arena and mask them out from their environment. With the objects identified and segmented from their environment, we could use that data to orient the robot to align with the obstacle. However, I still needed a way to estimate the distance from the block to the robot in case I had to retrieve the block. I created a bounding circle around the block in the camera frame and used the data from the y-centroid and radius of the bounding circle to create an empirical model with the block at different distances from the robot's camera. With the trend lines from the empirical model established, I could use this distance data to create a series of steps for DART to traverse as it closes in on a block. Before every forward step, it does take a moment to make a rotation to ensure that the block is aligned with the center line of the camera, which ensures that the block lies between the claws of the servo gripper before it makes a pinching motion. Here is the point of view of DART as it closes in on a block, opens its servo gripper, retrieves the block, and moves it to a new location.
To complete the grand challenge, our robot had to retrieve randomly placed colored blocks from a cluttered environment on one half of the arena and bring them back to a 4x4 foot construction zone on the opposite corner of the arena. The robot had to retrieve a red block, followed by a green block, followed by a blue block, in that order until no blocks remained outside the construction zone. This challenge had to be completed in 10 minutes, and if the robot brought back a block in the wrong order or made contact with a wall of the arena at any point, the trial was over. So it was definitely important to minimize the accumulation of error in position by localization so the robot knew where it was in the arena at all times.
To assist in integration testing, I tried to replicate the conditions of the arena as best I can in my apartment. I printed off a series of additional blocks using my 3D printer and then used duct tape to create a rough mock of the 10 by 10 foot arena. Here is my first run of DART in the newly constructed arena. It did have success identifying the green block and moving it to the construction zone thanks to my rigorous implementation of motion control. But now I had to actually define the autonomy protocol for dropping off the block and looking for new blocks in the correct order. To ensure positional accuracy, before I dropped off a block in the construction zone, I used the sonar sensor to get a ping of distance off of the two walls of the arena nearest to the construction zone. I also relocalized again before searching for the new block to absolutely minimize any positional error that could cause me to run into a wall. This test run had me feeling pretty good, even though it was hard to identify the blue block, but I definitely felt like I was ready for the grand challenge. Before we knew it, the big day was here, and we were all really excited to test out our robots and see how they performed in the Grand Challenge arena. We had the opportunity to do some testing with our robots in the Grand Challenge arena, and I was still feeling pretty good about my localization efforts, as seen here with the red block and how accurately it brought it back to the 2 foot by 2 foot position in the construction zone. At this point, all of the practice was over and it was time to put DART to the test in the Grand Challenge. DART started off pretty strong, collecting the red and the green blocks with relative ease. However, once it made it to the first blue block, it actually knocked it over with the bumpers because its estimate of distance when it approached the block was not very accurate. Despite this, it did recover and started collecting more blocks, but as it got to the second green block, it knocked that block over too. Knocking over the blocks ended up being an absolute killer on time, as the robot won't drop off the block in the construction zone if it's not in the correct orientation. Despite this, it did recover and continue to correct the blocks in the correct order, but unfortunately, it could only get 7 out of the 9 blocks before time expired.
So during the grand challenge, DART ended up retrieving 7 out of the 9 blocks before eventually exceeding the allotted 10-minute time frame, which means I did fall a bit short of my goal. However, relying on computer vision models in environments with changing lighting can definitely be tricky. And although I was pretty confident in my autonomy algorithms, I did experience errors stemming from a poor fit from my block distance model to colors of blocks other than the ones I used to create the model itself. Unfortunately, this means I might have to rename DART from DART to D.A.R., as although it definitely did detect and retrieve blocks, it did not do so very timely. Nevertheless, I had a great time this semester. I'd like to thank Dr. Stephen Mitchell for teaching the course this semester, and thank all of you for watching. Thanks.